third and final speaker today, this special session. So Mary Angelica Tursi, I think once upon a time of the University of Urbana in Illinois, is that right?
Yes.
Okay, and Mary is going to tell us about homogeneity and amalgamation in subclasses of Banach lattices. So please.
All right, well, thank you for inviting me to give this talk. I don't know how much the audience here knows about Banach lattices, but just think Banach spaces with like min and max operations like C of K or LP, and that follow who's that work nicely with the norm, right? So if you have an order, you have positive elements. If you have x and y, x less than or equal to y, and they're both positive, then the norm of y should be the norm greater than or equal to the norm of x. So, and they have really, really nice properties. So just think of those kinds of spaces when you think of Banach lattices. We also have the notion of ultra homogeneity. So in classical Banach space theory, you have the Gourage space that is separably universal for separable Banach spaces, but there's also this nice little homogeneity property in which if you have a finite dimensional Banach space A embedding into the Gourage space G, and A also embeds into B, then you can extend the embedding from A into G to an embedding from B into G with minimal distortion in the norm. And if you want to, but you can also embed B isometrically into G, but then you loosen up the commutativity requirements so that it's just an approximation in the norm. And it turns out that with the Gourage space, if you have a space that has either one of these two homogeneity properties, you are isometric to linearly isometric to the Gourage space. And so it's unique in being universal for separable Banach spaces and having this either one of those two properties. And one interesting thing about it is that it can be constructed as an inductive limit of L infinity n spaces. And in fact, this is one of that kind of construction is one of the earlier constructions for the Gourage space itself. So, but it obviously with ultra homogeneity, we don't have to limit ourselves to Banach spaces. We can look at other classes and the appropriate maps. So I'll just give a brief outline of some of those spaces. If you limit yourself to L2 of n, you can have you have the Hilbert space as ultra homogeneous, and not just approximately. You can have full commutativity and full and actual isometric embeddings for the Hilbert space. For Banach lattices, if you limit your maps to lattice isometric embeddings, so these preserve the lattice operations, you have LP of 0, 1 is approximately homogeneous for separable little LP n spaces. And then also the homogeneous AM space that corresponds to finite dimensional L infinity n spaces with this kind of homogeneity property. And these were shown pretty recently to have these homogeneity properties for Banach lattices and lattice embeddings. Also, there was a Banach lattice of universal disposition. So this was another term that's very similar to homogeneity. This space constructed by Aviles and Trasete it has full homogeneity, full commutativity in its homogeneity properties, but then you lose separability in order to be able to get that extreme level of homogeneity. But if you, again, allow some wiggle room in the commutativity, you can get an approximately ultra homogeneous separable lattice. And this was something I constructed last year. And the work for this talk is based on some techniques from the work that I did in constructing this script L. And like the Girard space, it is also an inductive limit of a certain collection of finite dimensional spaces, in particular L infinity and L of L1n spaces. So the main tool that is for each of these spaces, you can show that the classes of these small structures embedding into your big space, these classes have certain special properties, and we're going to go into what those are. And if you show that the class has these properties, in particular if the class is Freyse, then there is some universal structure that it also is homogeneous over the appropriate maps and the elements in the class. So, and this is based on the metric version of tools for model theory. So there's a little bit of logic here involved. So if you have exometric structures, so again, for all us Banach space people, think you have Banach space, you have operations like addition, scalar multiplication. If you have a Banach lattice, you throw in also the lattice operations, and then you also throw in like the norms. The norms are considered some operation in your language that you use to talk about Banach spaces or lattices or whatever have you. And so that's basically a metric structure. And if you take some subset A of X, we're going to denote by bracket A the substructure that is generated by the elements in A. So here you want the bracket A to be closed under the function operations in your structure. And you also want it to be topologically closed. And now if you have a finite and X itself is generated by A, then we just say X is finitely generated. So with Banach spaces, you have finite dimensional spaces. But Banach lattices, you can have all sorts of other lattices that are infinite dimensional, but generated by only finitely many elements. In particular, you can have, for example, the continuous functions on the delta set, any little LP space, or actually LP of 0, 1 also is finitely generated. And the script L, the approximately ultra homogeneous lattice, that's finitely generated by 2 elements. So much bigger collection of lattices that are finitely generated here. And so now if you have, say you have a collection then of these finitely generated metric structures, I am defining the structures by these tuples that generate the structures themselves. Suppose that my A and B are of the same length, and I'm going to define a distance between the tuples. And in the case of Banach spaces, just think of distance. And we can define something that looks like a metric for these structures generated by the tuples by taking the infimum of the element-wise distance when the tuples are embedded into some third structure in K. So the idea is that if these distances are small, then I can put them into I can put the generating elements of the structure with the appropriate embedding into a larger structure, and then these elements are going to be really, really close. Now, the thing about this is that being close does not necessarily mean that you are isomorphic in any way. So it just means that you can have something that's infinite dimensional be very, very close to something that's finite dimensional, for instance, with lattices. But it tells you that it just gives you a sense of how closely elements are related to each other within this class. And so given that, we say that a class K is Freyse if it satisfies the following properties. So there's about 5 of them. The first is that it has the hereditary properties. So if you have a finitely generated space and then a finitely generated subspace, that subspace is also going to be in K. Joint embedding property means that I can take any two structures in K and embed them into a third finitely generated structure in K. So, and this property guarantees that this metric-like operation D of K is well defined over all of K. And then the near amalgamation property. So if you have, basically the idea is you have some A embedding into B1 and B2, and these are all finitely generated, then I can find some C and K and some embeddings B1 from G from B1 to C and G2 from B2 to C, so that at least along my tuple, when I take the distances of G1F1 of the tuple A and G2 of F2A, then I can get as arbitrarily close as I like. So we don't need full amalgamation for this to work. We just need near amalgamation. Of course, you can get full amalgamation if you want, and we just say it has the amalgamation property. And then finally, we also include these two properties. The continuity property means that if I use my DK metric-like operation and I take a bunch of tuples that generate these elements, if I take a function of some of the elements of the tuples, that map is going to be continuous. And predicate symbols, so for Banach spaces, think like the norm, for instance. If I have a tuple, the map from a collection of tuples to the norm of, or some other predicate operation, that's also going to be continuous. And the last property is the Polish property, and which means that this D of K is separable, so I can get countably many representative generating tuples, and it's going to be DK dense. And also it's going to be complete. So if I have some sort of DK Cauchy sequence and it converges to some other tuple, that tuple is also going to be in K. Now, if I can loosen these restrictions to just have something that's an incomplete Freycinet class. So in this instance, I loosen continuity to Cauchy continuity. So this map takes DK Cauchy sequences to DK Cauchy sequences. And then for the Polish property, I only require separability, but I don't require completeness. And if K has these looser properties, we call it an incomplete Freycinet class. But as we'll see, that's actually going to be pretty strong still, because its completion is going to be itself Freycinet. And so the main big theorem about this is that if you have KF Freycinet class, then there is a unique separable structure with the following properties, that it's approximately ultra homogeneous. So if you take some structure generated by the tuple A into this script M, you have two different embeddings respecting all the operations and whatnot. And then there exists some automorphism over script M where that sends it sends FA arbitrarily close to my G of A. And so we don't have to get full commutativity, but we get arbitrarily close. And the second fact also is that the class of finitely generated substructures of the script M is itself K. So there's also a converse of this. If you have M approximately ultra homogeneous over any of its substructures, the finitely generated substructures of M, then that class of finitely generated substructures of M is itself a Freycinet class. So you can go back and forth on these. And it just shows you this sort of equivalence between looking at a class as Freycinet and the existence of some universal, approximately ultra homogeneous object for that class. So in this talk, we're going to look at two particular subclasses of lattices. One of them is the LP, LQ lattices. And I'm going to give a concrete representation of these. There's an abstract representation given by Henson and Raynaud, but the concrete representation is going to be what we're using because especially since we're dealing with separable structures here. So these lattices have a lot of nice model theoretic properties. And they act a good bit like they're, our typical LP spaces as well. So just to give a concrete representation of these, if you have measure spaces, omega sigma mu and omega sigma mu prime, we denote by LP of omega, LQ omega prime, to be a space of Bochner measurable functions. And these are functions f from omega to LQ of omega prime, and that are limits of maps to simple functions in LQ of omega prime. So you can take some element in omega and then you map it to some simple function in LQ of omega prime, and then you can take limits, and that gets you the Bochner measurable functions. But then we also have the requirement that the map from omega to f omega of q, the q norm, is itself, this function is itself an LP of omega. And you take those, you have what's called an LP of LQ space. And we can also think of these f of x as these functions as some sigma times sigma prime measurable function, and then the norm is something that looks like this. And now we can take the bands of these LP of LQ spaces, and so think of bands as sublattices that are closed under downward order and for which there exists a lattice projection from the bigger space to the smaller space. And the class of bands, we'll call it BLP LQ. This class is axiomatizable, meaning that I can have a collection of metric sentences that completely capture this class. And so that's just like a little fact that is, that's kind of nice, and it gives you nice properties. LP spaces are themselves like this too, but we don't have it's not the case for just plain LP LQ spaces. Now, one fact about these is that these BLP LQ spaces can, in some respects, be approximated by finite dimensional versions of themselves. So if you have X a BLP LQ space, I can take any disjoint elements and disjoint in the lattice sense, and any epsilon greater than 0, and I can approximate the lattice generated by these x1, xn's. This will be a finite dimensional lattice, by the way, by some sublattice, I guess, of a finite dimensional BLP LQ space, in the sense that it's very close to lattice isometric, and and it's also very close to the actual generating elements here. So just a visual representation of what that's like. I like to think of it as taking, you have like some omega and omega prime, and then this purple area is the omega times omega prime measure space. And if I take a band, it's like I can take some sort of blob circling around different portions of it, and that can characterize, at least abstractedly, a separable BLPLQ space like this, according to what's supporting the functions in that space. And it turns out you can concretely represent it in this fashion. Now, if I take the support of, say my support in omega and omega prime is strictly inside my little square here, there's no atoms in the measure space sense, then we say that such subbands are doubly atomless. And it turns out that there is, up to lattice isometry, only one doubly atomless BLP LQ space. And that's just the space LP of 0, 1, semicolon LQ of 0, 1. So just remember this little factoid because that'll come in handy later. So now let's look at how we can build up, show that the class of finitely generated sublattices of LP-LQ spaces themselves have these Frise properties. So we'll let script LPQ be such a, we'll name that our class, and this is going to be sublattices. It doesn't have to be strictly BLP-LQ. And then we will let script KPQ be the finite dimensional sublattices of little LP and little LQM spaces. One fact about this is that if I take this DKPQ metric-like operation, I take the closure of this and I get LPQ. And so what that means is that if I want to show that LPQ is Frise, I only need to show that this KPQ is incomplete Frise, because we already have that the closure of KPQ is LPQ. And so the main theorem that we need to show here is the amalgamation property. If you can easily have hereditary properties, that's pretty obvious. Joint embedding properties, pretty clear as well. The continuity, the Polish properties, you can come up with countably many, the weak continuity and weak Polish, you can come up with countably many of these KPQs that are going to be dense in my in KPQ itself. And then Cauchy continuity follows from the axiomatizability of Banach lattices in general. The operations have these moduli of continuity that are present regardless of the choice of Banach lattice. So really the only thing we have to do is prove amalgamation for KPQ. I don't know how much time I have, but I'll go pretty quickly in this. So basically we start off with some E, and it's going to be a subset of F, which is a finite dimensional BLP-LQ lattice. And so think of it as a p-sum of a bunch of LQMs. And we're going to let the atoms of E be, we'll just denote them by E1 through EM. And then we're going to let the atoms of F be denoted by UIJ. So if you take these LQ rows enumerated by I, and then J is going to be the jth atom of the LQ row. And basically what it comes down to is we're going to kind of collect different portions that are supported by different atoms. So if I'll let MIK be all the J's where the UIJs support EK, and then I can express EK in this fashion. So I add up over all of the rows, all of the BIJs, so these are the coefficients when I take my EK and map it into my F. Then I just take all the J's that are in the MIK and then add up over the rows I. And we're going to denote by capital BI with BIJ to be the Q sums of the BIJs when J is in MIK. And then I'm going to take all of these rows, and M, we're assuming M here is like the number of Q rows of LQ rows that we're adding up with a P sum. We're going to partition those rows into sets A1 through AN where two rows are in the same set in your partition if they are linear multiples of each other and they're non-zero. And then we let A0 just be all of the rows that are not supporting any of the atoms in E. And then for each of these A1 through AN, we define RK, which with RKJ being this this basically this PQ sum, P over Q sum, and then rooting by Q over P. And we're going to call this R. So we're getting like this matrix, basically, where the rows are up to constant multiples of each other, and the columns correspond to each of the atoms. And we'll call this matrix R a profile of E. And it turns out that when you have E mapped into any two different BLPQ, finite dimensional BLPLQ lattices, this profile is independent of the choice of your maps. And that's really helpful for us, because then what's going to do is allow us to come up with a pretty, a nice amalgamation construction. So we can kind of fully characterize these KPQ finite dimensional lattices with these profiles. And so the construction is kind of complicated. It looks kind of technically complicated, but once you have everything set up, it's just a matter of defining these G1s and G2s by taking your, you can take your, say your E is mapped into F1 and F2, and then I can take F1 and F2, take some some lattice tensor product, let that be my H, and then I can just express it in such a way that the commutativity works out and then norms are preserved. And the reason is because of these profiles R being used in the definition for both of these maps. So it's a bit technical. I don't want to go too much into it, but basically by characterizing these finite dimensional spaces, I can then also give a nice amalgamation construction. And so basically what that means is that we then have that KPQ is an incomplete Freyset class. So LPQ is Freyset, and it emits a universal, approximately ultra-homogeneous object. And as I mentioned before, the other Freyset conditions are pretty clear, and the same thing with the weakened versions of the Polish property and the continuity property. But one thing that we'll note here is that in order for this object to be approximately ultra-homogeneous, it has to be doubly atomless. If you're not doubly atomless, you might have LP as a band in your space, or LQ as a band, or some actual atoms. And when you're mapping, you can, that won't, atomness in some way won't work well with homogeneity. So this Freyset limit, this universal object, has to be doubly atomless, and up to isometry, there's only one such space. So that gives us LP of 0, 1, LQ of 0, 1 as our candidate, our only candidate for being the Freyset limit of LPQ. And this mirrors the case with LP being the Freyset limit of the little LPNs, and the little LPNs are themselves an incomplete Freyset class. So I don't have too much time left, but I'll go quickly into a different approach when it comes to the cases of script L infinity P. So if we let one of the PQs just be infinity, in particular the outer one, we get lattices that are P convex. And the technique here is a bit different, but what it comes down to is that you have a definition of P convexity here, and that's if you have this weird looking operation over lattices where you take xi to the p, sum them up, you get 1 over p. That the norm of that is less than or equal to the p norms of the xi's. And now this expression can make sense if you're dealing with an order continuous lattice. It would be, because then those kinds of lattices are vector lattice ideals in some function space, and then you could just take component wise, you just let the component wise values for these functions determine what this xi to the p of 1 over p is. Or if you're dealing with a C of K space, this also makes some sense, right? But if you have an arbitrary lattice, this might not immediately make much sense, but you can use a functional calculus approach to express what this thing is. And it comes down to taking the supremum of the moduli of the xi's, taking an alternate norm, which is itself an L infinity norm of sorts. And then this means that this vector sublattice equipped with this new norm is going to give us something isometric to a C of K space. And that's going to give us an element that makes sense of this xi to the p summed up and then taking 1 over p of that. And these coincide for this expression coincides independent of your choice of supremum element. It doesn't have to just be z equal to the norms I of xi. It could be something bigger than that. Or if you're in the order continuous world, when you do this operation, you're going to get the same thing. So this expression ultimately makes sense when you do some other representations. Now, if you have a lattice E, there's a sort of canonical way to generate a p-convex version of E. So you have the same underlying set, but then you replace your addition and multiplication operations while keeping the lattice operations with new ones, so that and you take a 1 over p of the norm, and this will give you a p convexification e to the p. And so there's a sort of canonical way to map E to some p-convex version of it. And you can also go backwards, right? If you have E p-convex, I can do something to this E that makes it lose its some level of p-convexity in a sort of canonical way. And it turns out that these operations are inverses of each other. And they correspond to some nice expectations. So if I take the p convexification of this C delta of L1 0p, if I take the p convexification of that, this lattice I'm putting here because it's also separably universal for Banach lattices, I then end up with C delta LP of 0, 1. And so I have a few minutes, I'll just be really quick now. But basically, this p convexification works as expected. Take the Q convexification of a P convexification, and I'm allowing this to be just greater than 0. So if you have something less than 1, think of it as that inverse operation for the 1 over P. Then I get back to my original lattice. This convexification also preserves lattice embeddings. So if the map T e to F is going to be a lattice embedding, then the same map, because remember the underlying sets are the same, from E to the P to F to the P is also going to be, that's still going to be a lattice embedding over the new operations. And if you have something that is finitely generated, then it's going to be finitely generated in the P convexification. And using these preservations of embeddings and the way the convexification works, all I need to do is go back to my original Banach lattices that are finitely generated, and then just go back and forth between P convexification and going back to the originals if I needed to show that the class KP of finitely generated P convex lattices also has things like the amalgamation property, is if I say class in general. And you can use the same argument to show then that it's an inductive limit of these L infinity and LP of n spaces, just like the script L lattice was an inductive limit of L infinity and L1 n spaces. So we have corresponding homogeneous objects depending on your P convexity. And so that's it.
Thank you very much for that beautiful talk. Do we have any questions, please?
Yes, Mary. There, you had a restriction in Theorem 5 that P cannot be a multiple of Q. Why does this come up?
Oh, okay. So basically, let me see. I think it comes up here. So when constructing these profiles and showing that the profiles are the same independent of the choice of your map, I mean, up to some permutation over the rows, of course. The way I ended up proving that involved it's kind of funny. It involved some multivariable calculus. And what I needed to do was to show that if I have, regardless of my constants, that I preserve norms. If you have something that's P over Q, then things could bleed in, basically. If you don't, you can then show that certain elements have to be the same. And that's basically how this comes up. Now, I haven't checked yet what happens in the case where P over Q is in.
We lost you.
Yeah, looks like we lost.
Yes, it looks like we've lost our speaker.
Defense contractors finally got into this conference.
I saw this was dangerous to say this is the natural.
We're never going to find that why P over Q can't be a natural number.
Right.
Q doesn't want it. That's an interesting restriction, though.
I think we may have even lost our speaker now, right? If I'm.
We don't. Yeah. Yes. Now we even lost the.
Yes.
Talk,
I think
right?
she's totally. I think she's completely lost her connection now. And there we have it. Hello, Mary. Thank you.
back.
Welcome back.
Right.
Hello. There was a connection issue. Are there any other questions or?
So is there a counterexample when, say, P is 4 and Q is 2?
I'm unsure. Oh, for my case?
Yes.
I haven't checked yet. That's like the next thing that I want to check and see. But yeah, I'd like to check and see if there's some tools I use there and right project.
Okay. Are there any more questions? I think we may have time for another quick one. If that's not the case, then let's thank Mary and all of our speakers today again.